So it's my pleasure to introduce Dimitri Denisov as today's colloquium speaker. Dmitri received a master's degree from the Moscow Institute of Physics and Technology and a PhD from the Institute of High Energy Physics in Podrino. He joined the D0 collaboration in 1987 and Fermilab in 1994. So during the first Tevatron run, he played a major role in the discovery of the top quark at the Tevatron and later carried out a precise measurement of the bottom quark production cross-section. Dmitri led for a long time the group responsible for the D0 muon chambers, which played an important role in both of these physics topics. And then he was in charge of commissioning the D0 detector for the second Tevatron run and later led the electroweak physics group. In 2006, Dmitri was elected co-spokesperson of D0, and he has served in that position with varying partners since, and shepherded the D0 through this important transition of stopping the data taking and so on, but continued still a lot of work on analysis and still publish a lot of papers. In 2019, Dmitri moved from his position as a distinguished scientist at Fermilab after, I guess, 25 years at Fermilab to join Brookhaven National Lab, where he is the Deputy Associate Lab Director for High Energy Physics and responsible for Brookhaven's strategic planning in high energy physics. So Dmitri has been a friend and a mentor to me since my time in D0, and so I'm especially looking forward to today's colloquium, in which Dmitri will talk about the top quark, of course. So ever since its discovery, the top quark has been a treasure trove of information about the Standard Model, and its study is still pursued and expanded, in fact, today at the LHC. Recognizing its importance, the D0 and the CDF collaborations were awarded the European Physical Society Prize in 2019 for the discovery and the study of the top quark. So Dmitri led D0 through a good stretch of this endeavor, and we had originally invited Dmitri to give the A.O. Williams lecture in the spring this year, marking the 25th anniversary of its discovery. The announcement was in March 1995. Unfortunately, like so many things, the coronavirus pandemic threw a monkey wrench into these plans, but I'm happy to finally see Dmitri and being able to welcome him to Brown, even though it's virtual only, to finally give the colloquium about the top quark. So welcome, Dmitri, and you should share your screen.
Okay, well, so thank you very much for such nice introduction. So it's a pleasure, as always, to see my friends and colleagues from Brown University. And if you hear me well, do you?
Yes, you're very good.
Okay, then I will start. And I hope you can see my screen. Just checking. Good. Okay, look, thank you for the introduction. This year is indeed special for the top quark because it was discovered a quarter of a century ago. As earlier already pointed, so I was planning to come and be in person with you in March, and that was exactly the month when the announcement of the top quark discovery was made 25 years ago. COVID changed these plans, but I'm still hopeful that in just hopefully a few months, the life will come back to close to normal and we will be able to travel. Also, as a comment, I would say that as you will see from my talk, where I will talk about past, present, and future, majority will be on examples from the Tevatron program. That's where I was deeply personally involved, although I will show quite a few results from LHC, which is currently the only place on the Earth where top quarks could be produced in large quantities. And of course, I would like to thank many of my Tevatron and LHC colleagues for input, slides, and plots distributions, which I will use in my presentation. With that, let's go back to early 1960s when the Quark Model started to be created. At that time, there was a zoo of particles which were created with different masses, with different properties, which was very hard to understand and make any specific conclusions. In 1964, Gell-Mann and Zweig proposed quarks to explain hadron spectroscopy using just three quarks, U, D, and S, a strange quark. And using these three quarks, majority of these hundreds of elementary particles were able to be explained. That was a great success of the Quark model. But also it brought some challenges, for example, absence of labor-changing neutral currents, which led Glashow, Leopoulos, and Mayani to propose a fourth charm quark to form an analogous isodoublet. And starting in 1974, hadrons containing charm quarks were discovered. So by mid-70s, basically we had very symmetric picture of leptons and quarks. You can see on the bottom of the slide, with four of each discovered, and majority of effects which we saw at colliders explained by this simple picture. But then things started to change. So first, just a year later in 75, a new lepton, so-called tau lepton, was found in slag. That's a heavy cousin of electron and muon. And its neutrino partner, nu tau, was in ferrite. Now you can see here the picture of this small collider at slag, which had enough energy to produce tau lepton, as well as J-psi particle for Quark Discovery. Then another 2 years in 1977 at Fermilab, in the effective mass spectra of two muons of opposite signs, the team led by Leon Lederman discovered resonance which appeared to be bound state of B and anti-B quarks. So basically by late 70s, picture of elementary particles, building blocks, quarks and leptons looked like what's shown on the top right here. And it's clearly that something in this sort of nice symmetric picture is missing. So something in the top right corner. So, that's where the race for the top quark started. Of course, there were many different assumptions about the mass, because this is one of the most critical parameters which defines what kind of accelerator or collider you need in order to produce such particles. And naive expectations based on the mass, for example, of C quark and B quark, says that top is probably about 15 GeV. So you need about 30 GeV in the center of mass to produce pair of such particles, hadrons made of this. By 1984, Petra Collider in Germany ruled out top quark with mass less than 23 GeV. So it was expected, but then new plus and minus collider was built in Japan called Tristan with energy up to 60 GeV. So everyone was expecting to see bump in effective mass spectras or in the cross sections of TT-bar production, but this did not happen. So, and by late 80s, a limit above 30 GeV was set on the mass of the top. So where is the top? So lab experiments, the highest energy plus and minus collider increased the limit to about 46 GeV. In 1990, UA2 collaboration, so which was using proton anti-proton collisions at CERN, which were useful to discover W and Z bosons, set a limit at 69 GeV, effectively closing the third channel when top was product of the W boson decay. In 1992, CDF at the Tevatron now searching for TT-bar pairs production with top mass above W mass set limit at 91 GeV. So it's pushing. Remember, we were thinking, so it's supposed to be 15, it's 91 by now. And in 1994, D0 experiment joined the party and set the last top quark limit before the discovery at the whooping 131 GeV. So, of course, main role in the discovery of the top quark was played by the Tevatron. Fermilab first accelerator was built in 5 years between 67 and 72 and had the energy of 450 GeV for the protons. It was a 6 kilometer long ring, so you saw it on the picture on the first slide of my talk. In 1978, the decision was to build one TeV superconducting, the first superconducting fixed target accelerator. So it was not a collider yet, but it was accelerator with proton energy of 1 tera-electron-volt, and with the option to develop into collider. But by 1981, the doubler, and that's what was the name for the superconducting accelerator, because it's about double energy of the original accelerator, construction was progressing well. And Tevatron 1 project, colliding beams, it was called Tevatron 1 project, got the Department of Energy budget. It was not that easy because it's required sort of superconducting magnets filling 6-kilometer long tunnel, and it will require a source of antiprotons because the idea behind the Tevatron was that the same basically beam pipe, the same magnets in one direction rotating protons, in another antiprotons, and they're colliding in a few places in the ring. So again, the matter-antimatter asymmetry to a very high precision allows you such tricks when you're using the same magnetic field, same electric field accelerating protons and antiprotons moving in different directions. But of course, making large number of antiprotons was a major challenge. And here you can see some schemas of the first design of the antiproton source at Fermilab. This is 1983 now, so it's the last Tevatron magnet installed. Helen Edwards, who was leading this project, is signing installation plaque. What certainly tells you about 1983 when I was looking on this photo is that the person behind Helen, who is Thornton Murphy, who was one of the physicists working on the project, is actually looking on his box of cigarettes. So that was a time when people did smoke in various places, including in the Tevatron tunnel. Okay, next slide shows you antiproton accumulator construction in December 1983. So even during cold Illinois winters, so the construction was progressing because everyone needed a large number of antiprotons. Not that easy to make them, so you put protons on a target with probability about 10 to the minus 6. With the energy of the beam about 150 GeV, you will have antiprotons. So you have to extract these antiprotons, make a beam of them, cool them down to get very small diameter beams. So it's a whole exercise of making antimatter. But at the end, Fermilab was by far the largest place in the world which produced more antimatter by orders of magnitude than any other place, including CERN. So the central players are the accelerators. So you can see on this picture sort of the big Tevatron ring. The main ring, the original 450 GeV warm magnets accelerator was used at very low energy, 150 GeV, about 30%, to put beam on the antiproton production targets. And then there were various accelerators which were used in order to accumulate and later inject the antiprotons back in the Tevatron ring in the opposite direction. And you can see here also two experiments, CDF and D0 in orange and blue. So that's the color of the buildings. And that's how the teams were called during the Tevatron days, which were designed and built in order to detect this ultra high energy, about 2 TeV in the center of mass collisions. These are Tevatron Run 1 performance plot, so which was between 1992 and 1996. You can see that the peak luminosity was, in comparison with today's 10 to the 34th LHC, is very low, look in the range of just a little bit above 10 to the 31s, orders of magnitudes lower. But nevertheless, it's provided opportunity to produce large number of top quarks, as you will see later. And of course, even with such luminosity interaction rate, and this is how many interactions you have per beam crossing, which is creating many challenges for the modern hadron colliders, including LHC, was not an issue at all. We had an average well below 1 interactions per crossing, even with 3 microseconds beam crossing. Of course, experiments was also the key to get to the top Quark discovery. And I would say Tevatron and D0 following UA1 was sort of modern class collider beam experiments. This is schematic of CDF experiment. had excellent tracker in solenoid magnetic field, extensive calorimetry, and additional for the first time at Hadron Colliders of Silicon Vertex Detector to tag the big quarks, which you can do using the lifetime of the hadrons, which have a lifetime of approximately 1-2 picoseconds. As a result, they can travel a few millimeters, taking into account gamma factor, and that could be detected in high precision silicon trackers. So let's move to the second experiment. This is D0 experiment. It was proposed a little bit later in 1984 as a second large Tevatron collider. It had very hermetic calorimetry and muon system, while no central magnetic field. Amazing. So there were no opportunity in round one of D0 to measure charge of the particles which were created or or measure their momentum. So basically for the jets, you measure and photons and the electrons, you measure energy in calorimeters. For muons in the muon system, with moderate precision. But overall, sort of, it was an interesting experiment which was constructed and built at Fermilab. Let's keep now moving to what top quark discovery. So the channel which Tevatron used was top anti-top quark production. So you can see it on the top right side of the slide here. So you produce pair of top anti-top quarks, and then in standard model with almost 100% probability they decays to the W boson and B quark. And then W decay into either leptonically into, let's say, electrons, muons, tau, and appropriate neutrinos, or a pair of quarks which usually create jets. And this is how, depending upon the decay of the W, this is how different channels of the top quark pair production and decay call, like dilepton, when both W's decay leptonically, lepton plus jets, when one W decays hadronically and one leptonically, or all hadronic when you have many jets in the event. And jets are results of hadronization of the quarks or gluons in the detector. So let's keep moving, sort of starting by 1993, with a few inverse picobar, CDF and D0 started to see very interesting events. This was a time when scientists did look on event displays and extracted a lot of information from them. On the left, you can see one of the first top-like event displays from CDF, on the bottom from D0. And this bottom event was really striking with very high PT, electron and muon, missing energy, which corresponds to neutrino escaping from the W boson decay, as well as two jets potentially coming from the B quarks. So on the next slide, you can see sort of, I would say, visual in subatomic world. It's not maybe a bubble chamber. Everyone likes these bubble chambers with bending tracks and omega discovery here at BNL. But I think that this event display taken in 1993 by D0 also is amazing. Look on the right on the diagram. So you have two big quarks, two W, one W decays into muon and neutrino. And you can see on the top, again, the muon track reconstructed in the central tracker and as minimum ionizing deposits in the calorimeters. That's a muon track. Now, second W decayed into the electron, and you can see on the bottom is a small cluster of energy in the electromagnetic calorimeter, which is identified as electron, including track. And then you can see two clumps of energy, which are jets, which most probably came from the B jets in this event. So it's actually very nice visualization of some very interesting events which are happening on subatomic distances, how they look in the large particle detectors. So towards the discovery, so in early 1994, so CDF published analysis based on approximately 20 inverse pecobarns, which was called Evidence for the Top Quark Production. There were quite a few events in this analysis which looked different than typical backgrounds. For example, W boson and jets production from QCD. You can see on the bottom left plot that the number of events above expected backgrounds and this shaded area is expected background. Yeah, you can clearly see in the areas where you expect more events from the top quarks with large number of jets. some excess of events. Distribution, for example, in effective mass for this event looked very much top-like. And if you look on the cross-section versus top mass, remember, nobody knew top mass at that time, except that it's more than 130 GeV. You can see that the point sort of which obtained, it's a little bit above, sort of the history showed CDF was a little bit lucky with upward fluctuation of the number of events, but it's sort of in the proper, approximately right area. So that was certainly very exciting, but will it sort of materialize or not? It was not yet clear. And the clarity came in early 1995 with the top Quark Discovery. On the top, you can see the basically the PRL paper announcing the discovery by CDF. You can see sort of it was quite a few events. CDF found 6 dilepton events and 43 lepton plus jet events. Among them, there were 50 B tags. Of course, in some cases, you tag both Bs, in some just one. But nevertheless, sort of the mass of the top was measured to be about 175 GeV, not far from where it's now. Cross-sections became pretty reasonable in comparison with expectation. And background-only hypothesis was excluded at 4.8 sigma, which is close to the current standard of 5 sigma for the discovery. By the way, these famous 3 sigma and 5 sigma numbers were introduced by PRL as sort of a rule of thumb after the top Quark discovery, just to set sort of limits of 3 sigma because and 5 sigma to remove all possible confusion and arguments sort of what is discovery and what is evidence. And this is top Quark discovery paper title from D0, very brief, observation of the top quark. That's where I learned that, look, really famous titles have to be brief. D0 didn't have nice B tagging capabilities, although we did tag some of the jet with the soft muons, because in some cases, big quark have soft muon in about 10% of cases in their final states. So the number of events is shown here. There are 17 events. Background was about 4 events. Mass was on a little bit on the higher side, cross-section in good agreement with the standard model. And background-only hypothesis was rejected at about 4.6 sigma level. So you can see on the effective mass spectrum in the left part of the slide that there was one event at about 260 GeV, very high energy event, which actually pushed the top mass substantially in comparison with the current measurement of 175. Those who were at D0 at that time, including David and Uli and Meenakshi, remember all the arguments, should we keep this event or not? At the end, we followed the science, we kept all events which were in the pre-selection, and it's where we ended up. You always have small fluctuation on small data sets. And this is March 1995. About 1,000 of scientists came to the Fermilab auditorium to listen to seminars from CDF collaboration and D0 collaboration about announcement of the top Quark discovery. It was a very exciting time with a lot of newspapers covering this event. On the top right, you can see picture of the Fermilab director who was responsible for the accelerator part of the program, and 2 spokespersons from CDF and D0 who presented the discovery talks. Of course, you also can see here some of the D0 PhD students in 1995. So many of them look very young, and that's, of course, was also, without them, no discovery could be made because they really contributed strongly to this discovery, and as you know, in the longer term future, to many other discoveries in the field. Another point which I would like to make here is that, of course, this discovery was one of the first made with large international collaborations. So contributions from hundreds of scientists from all over the world, Americas, Europe, Asia, were critical for success. And you can see this flags and many people from various countries who contributed to the discovery. So now discovery been made. So with the new particle firmly established, so by 1995, nobody was expecting any anything sort of special in this area. Physicists were eager to study the properties of this particle. Production cross-section, various decays modes of this quark, mass, charge, spin, all of that sort of, you have a new toy. So you would like to test it, and the top quark also became a tool to search for new physics, looking for deviations from various theoretical predictions. Tevatron was the only place to study top quark till LHC startup in about 2009, or about 14 years after the top quark discovery. With a total data set of about 10 inverse from Tabarn by the end of Tevatron operation in 2012, Tevatron data samples reached 1,000 events level. Upgrades of the Tevatron experiment for Run-2, which was for 12 years between 2000 and 2012, were critical to improve many of top quark measurements. And actually, many of our optimizations of the detector for Run-2 were based on the better detection of the top quarks. Of course, LHC with its modern detectors and much higher collision energy and luminosity produced says about 10 top quarks every second. So it's really amazing. So it's I would say almost top quark factory. Many measurements are by now systematics limited. So while of course first measurements were severely limited by statistics. There were major upgrades to the Tevatron complex in late 1990s. In comparison with the Run-1 picture, you can see second ring on this picture. That was the main injector, 150 GeV rapid cycling proton accelerator to increase anti-proton production rate. And it also has permanent magnet recycler ring to recycle antiprotons after they were used in the Tevatron. So the idea was to decelerate them, put back into this ring, and then start again. It was never used in this mode due to various technical challenges, but it was used to cool antiprotons using electron cooling in order to increase collision rate of the Tevatron. So, and of course, Tevatron got a little bit higher energy by cooling down magnets to lower temperatures. Both experiments underwent upgrades. So both CDF and D0. D0 got central magnetic field, silicon tracker, of course, to detect the big quarks and particles containing them. But CDF increased their muon system coverage, improved calorimetry. So not surprisingly, both experiments for the Run-2 became much more similar in comparison with Run-1. So because everyone was trying to improve where some weaknesses existed in the original design of the experiment. So, but my silicon detector, central magnetic field, hermetic calorimetry in muon systems, as you will see, that's the same ideas which are used basically for all collider experiments on hadron colliders or lepton colliders from then up to now. Of course, Large Hadron Collider is important. I will start showing some of the results soon about LHC top quark studies. It's a 27-kilometer ring near to Geneva. You can see it's on this picture. It's deep underground, so you couldn't see it that easy. So it's going about 100 meters under the surface. Currently, it's colliding protons at 13 TeV center of mass energy and luminosity because it's proton-proton collision above 10 to the 34. So it's 3 orders of magnitude higher. There are 2 modern general purpose detectors, Atlas and CMS. They're much larger and more modern than, of course, CDF and D0, which were originally designed more than 10 years before Atlas and CMS even started the discussion about the design. But overall, they look similar in terms of major building block of these experiments. Looking on the right, you can see that, of course, one of the main advantages of LHC is substantial increase due to the energy in the cross sections and then the number of events. Like for the top quarks, it's almost 3 orders of magnitude in the cross section of the top quark production from the Tevatron to the LHC. And then it clearly helps a lot with the size of the data sample. So what kind of top quark studies? So on the right, you can see sort of that when you produce pairs of the top quark, you can do many different measurements. You can measure mass of the top quark, you can measure charge, you can measure decay modes. In all of that, you are comparing with predictions of the standard model. You can also look on the various decay modes. Are they in agreement with the standard model? And if not, maybe this is a way toward physics beyond the standard model, which of course will be very exciting to see. Also on the bottom left part of this slide, you can see sort of how the discovery plots with just on the left scale, 1, 2, 3 events changed. And even by the middle of run 2, this is CDF plot with about 5 inverse femtobarn. We're talking about hundreds of events with the top quark production and decays, which of course changed the game in terms of the abilities of the studies of the top. So how the top quark is produced? We already mentioned it briefly. Here, a little bit more details. At the Tevatron, it's produced through strong force pair production. You annihilate quark and antiquark, for example, and then the gluon splits in the top and anti-top quark. It's about 85% of the total number of top anti-top production. About 15% goes through gluon fusion, as shown on the bottom part of this plot. The right plot, and as you can see, it was done before the Higgs discovery. So I found this plot from about 2011. I put the arrow where the Higgs belong. But the point here was to say that top quarks at the Tevatron are produced not that often. For one top anti-top pair, 10 to the 10th collision, elastic collisions occur. So selecting these events from the backgrounds is not that easy. Although, of course, striking signature with very heavy 2 particles produced helps with the detection of the top quark. So decays, as we discussed, the top quark decays 100% to the W boson and B quark, as you can see here. And then depending upon the decay of the W, there are dileptons, which have pretty low backgrounds because it's a pretty striking signature with 2 high PT leptons, large missing energy due to neutrinos, which escape, as well as 2 big quarks. Lepton plus jets is the most copious channel, which is used for many, many studies. So it has relatively low background, but also provides opportunity to reconstruct basically everything in the final state. Look on this sort of nice diagram. So the only missing particle in the final state is neutrino, and it could be inferred from the missing energy, which you can measure in your detector. So basically, you know the direction energy of all final state particles, so you can reconstruct, of course, with some uncertainties, what was produced in this event. All jets also have information about all final state particles, including both W decay into jets, but it has substantial backgrounds from various QCD production. So let's start from the top pair production identification, and let's measure top cross section. So actually, it's pretty easy. So on the top right, you measure number of top events, subtract backgrounds, divide by luminosity, and efficiency of the top quark detection. Efficiency you do using Monte Carlo, luminosity you measure it with different tools, and the accelerator provides you some information on that. And then you count number of events and estimate backgrounds using either Monte Carlo or some data-driven methods. So here on the left, you can see sort of steps how you basically come to measuring the top anti-top production cross sections. After selecting events with high PT lepton, at least 3 energetic jets, we're talking lepton plus jets channel, 2 jets B target, and substantial missing energy from neutrino. On the right, you can see in the red, you can see the top. So you select number of jets more equal to 2. Basically, almost all your events are coming from the top decays. With 1 jet, yeah, so there is some small backgrounds from other processes. So almost pure samples of top quark events were produced and detected, and that was the idea how to identify the events with top quarks. So this is a plot of top quark production cross sections at Tevatron. You can see 2 experiments, various channels, dileptons, lepton plus jets, but all of them are in a pretty good agreement, reaching accuracy of about 5%. Large fraction of that accuracy of the luminosity of the Tevatron, but there are some other uncertainties which caused these uncertainties to be around 5%. This is one of the slides where LHC results now come to play. This is a cross-section of top anti-top pair production versus center of mass energy. You can see all points for the top on the left side, and this curve is for proton anti-proton production. The other curve is for proton-proton production. At some points, they almost the same. But here, of course, because of quark anti-quark annihilation, the proton anti-proton actually are better than proton-proton collisions. You also can see that a very wide range from the Tevatron energies all the way to 13 TeV. The measured cross-section are in good agreement with the theoretical predictions. And that's a good indication that the particle which was discovered is indeed the top quark, and its properties are in a good agreement in wide energy range with theoretical predictions. But top quark could be produced not just in pairs by strong interactions, because strong interaction can only produce pairs of the top quarks, but it only could be produced singly. There are two main channels, I would say three, but at the Tevatron, we were sort of concentrating on two, the so-called T channel, because it looks like the T, and S channel. So in this case, sort of the top quark is produced together with another quark and big quark, which shown sort of on the bottom of this diagram. And the S channel, it's basically diagram opposite to the decay of the top to WB, but it's not just when W can decay into the top and B quark. So you can see also the different modes because of the different incoming particles collisions differ at the Tevatron and LHC. So T channel is major at both Tevatron and LHC, but for the S channel, LHC has substantially a smaller fraction of events versus Tevatron. And of course, TW for the Tevatron was practically inaccessible because cross-section is so low, while it was detected by LHC. So it was not an easy, so it's more difficult to detect single top quark because total energy deposited in the event is twice less. It's just one top quark. It decays the same way, but the signature is less striking than two top quarks. And that's why it required combining CDF and D0 data, considerably more data, and use of multiple multivariate analysis and method to discover single top quark. So this is a single top quark production. So you can see on the left the final Tevatron Run 2 single top quark summary. So you can see that both experiments see it. So the cross section overall, these are data points in line with predictions, which are gray zones, theoretical predictions. What's also interesting, because in single top production, S channel, you directly measure the WT vertex. So you can, from the cross-section measurements, determine directly VTB matrix element of Kobayashi-Mascavo matrix. And this is what right plot shows the limits and direct measurements of this important matrix element at the Tevatron. Everything was in a very good agreement with the standard model after these measurements. These are single top quark production cross sections. Now combining Tevatron and LHC data, different modes, S channel, T channel, and W boson and T production. And as you can see, in a very wide range, there is a good agreement between theoretical prediction and experimental measurements. So we now understand how to make top quarks. So we can make them using strong interaction. We can make them using electroweak interaction. So I think that this is very amazing sort of how initial sort of handful of events produced by strong interactions at the end, we were able to learn so much about this heaviest elementary particle. Let's talk a little bit about top quark mass measurement. In fact, mass is one of the most fundamental and probably the only fundamental parameter which we have to measure. All other parameters of the top quark, you can either sort of like spin, whatever the theory predicted, you check that they agree. But mass of the top quark is very important, and the only way, except for indirect measurements, is to measure it directly. Top quark mass is measured using decay products in many different channels. One of the most accurate lepton plus jet channel. I explained you that in this case, you know everything about the final state particles, although of course there's still some confusion. Look on the cartoon on the right. So you have two big quarks, sort of two big jets in the same event. So when you actually measure two big jets, you don't know which one belongs to T or which one to anti-top quark. So it's always, there are some complications in these assignments, but nevertheless, on the left, you can see, for example, D0 measurements of the top quark mass. And by 2014, the accuracy of the measurements become on the level of well below 1%, or in this case, 173 plus minus 0.7 GeV. So one of the main challenging, most challenging parts here is to measure energy of the jets, this spray of particles with many photons and pions and other particles, to measure it with very high precision. Of course, the help here is that, as you can see from this diagram, in the same event, W with very boson, with very well-known mass, decayed into two jets. So you have calibration inside your event to ensure that overall calibration of your energy scale of jet is correct. Another interesting measurement shown on the right here on this slide, and this is first measurement of quark antiquark mass difference. The idea here is that, of course, because top quark is decaying so quickly before hadronization, and you have W boson, which carries the sign of the top quark, and lepton, which carries the sign of W. So you can determine which quark comes from, which decay products come from the decay of the top or anti-top quark, and as a result, measure mass of the top or anti-top, of course, with some probabilities. But here on the bottom, you can see one of the first results with about 4 inverse femtobarn by D0, which clearly indicated that within fraction of a GeV, the mass of top and anti-top quarks are the same. And since that time at LHC, these measurements became much more precise with accuracies in the range of a few hundred MeV range. But yes, top and anti-top quark mass are the same. This is a top quark mass measurement. So it was combination between LHC and Tevatron back in 2014. We're still discussing maybe another combination in the coming year or two. As you can see here, sort of all measurements in various channels by different experiments in America or in Europe are all in agreement within the uncertainties. And what's also important that by now, the accuracy of measurement is systematics limited. It's not number of top quarks, but it's again like calibration of jet energy scale, various Monte Carlo predictions, which are important. So, but going beyond this accuracy will be very challenging, and there are other ways, as we will see a little bit later, of going further. But you can also measure top quark mass from cross sections. Interesting, because the top quark cross section in standard model depends on the mass. On the left plot, you can see the red curves. This is the predictions as well as uncertainties. And of course, the cross sections which we measure do depend upon the mass, because to measure, for example, efficiencies of the detections of the various decay products, you have to simulate in your Monte Carlo the actual mass of the top quark. So each cross section measurement is given at a specific mass. So you can see these two curves have overlap. So this is interesting direct measure without measuring decay products properties. You just count number of top quarks. The measurements, one of the first measurements from D0, about 170 GeV with relatively large uncertainties, but still fully confirming the measurements in other channels. There are many other ideas how to measure top quark mass, and we will talk about some of them later. We will talk about future high energy colliders. There was excitement at the end of the Tevatron run too, and that was in measurements of forward-backward quark anti-quark asymmetries of the top quark production. So no forward-backward asymmetry expected in gluon production of the top quark on the left, but in quarks, there is some contribution to asymmetry via interference at the next to leading order. So there are a little bit more quarks and antiquarks going in proton directions versus anti-proton directions. Some new particles like oxygluons could change forward-backward symmetry substantially. In 2009, CDF measured this AFB parameter, which shown sort of on the bottom, and you can see even by eyes that there are more events to the right than to the left. So they actually saw that for some masses of pair of tops, the asymmetry reaches like 30%, and theoretical predictions at that time was a few percent. So is it finally we start to see some deviation from the standard model? As you can see from the next slide, after many more measurements of the asymmetry was updated, and substantial increase in improvements in the theoretical predictions, there is actually agreement. On the left, you can see sort of this, look, I would say grayish bars, theoretical predictions, and they're reaching at some values, for example, of effective mass, something like 20, 30%. Before these measurements, they were well below 10%. You can also see these triangles, which were original CDF points, they stays. So, and you can see like you can get exciting, but when you add other measurements, like for example, from dileptons at CDF or from D0, you can see that, look, agreement with the standard model is pretty good. So two lessons from that: many standard model theory predictions require correction. So just when someone tells you standard model predicts, sometimes it's a very complex calculations with many parameters, so it has to be done well. And of course, two experiments are also very important to verify and cross-check, especially at the limit of low statistics. So here are some of the top quark properties measured at the tevatron. We will not go through all the list, sort of, but it includes large, and it's only some, so there are actually close to 100 papers just from D0 published on the properties of the top quarks. And everything here agrees pretty well with the standard model. And what I would say is that it is very well-known quark by now. Of course, mass is one of the major properties, but for example, many predicted resonances between top and anti-top. Similar, like there are resonances between C and anti-C quark or B and anti-B quark. So this is how, again, J psi and epsilon were discovered and appropriate quarks were discovered, but none at this moment at the tevatron up to 800 GeV and up to much higher masses at the LHC. So top quark is indeed special and decays very quickly. So the results of the top quark mass measurements are very important. There are 2 points here. First, they provide high accuracy fundamental nature parameter, as we already discussed. So it's really has to be measured with as high precision as possible, and it will be in textbooks for many, many years to come. It's also critical for self-consistency check of the standard model. On the left here, you can see the self-consistency check of the standard model using mass of the W boson, mass of the top quark, and mass of the Higgs, which is green and bluish. And as you can see, after especially the Higgs discovery, when the Higgs mass was measured with high precision, so again, all of them agree with within about 1 sigma. So this also tells us that, look, the model which we have to describe subatomic wall is actually very self-consistent. But it's also interesting that mass of the top quark and mass of the Higgs are together responsible for the stability of electroweak vacuum state of the universe. And you can see here the diagram with vacuum being unstable, metastable, or stable. And you can, with current values of masses of top and the Higgs, and I don't expect they will change drastically, we can see that we most probably live into the metastable world. So it's an interesting observation which connects subatomic world and our universe at the largest distances with subatomic world at the smallest distances which we can study. This is an interesting plot which I would probably present mainly for our LHC colleagues, how more data open new opportunities. So of course, LHC is just at the very beginning. It's like tevatron was in early 2000s when top discovery was made in 1995, as you can see on this plot, and then run 2 started increasing luminosity by almost 2 orders of magnitude. And you can see how many different interesting measurements in top quark, and not just in the top quark sector, including excitement of top forward-backward asymmetry at the very end of the run, will be happening. So look, I would really wish good luck to LHC colleagues with many more exciting measurements and hopefully discoveries to come from the LHC. Now let me switch to some observations, some of them recent at the LHC with the top quark, which could not be done at the Tevatron because of the limiting energy. Top quark is too heavy to measure its coupling to the Higgs boson by Higgs decay, like we're doing for the big quark coupling, so other particles couplings. Observation of TTH production, and you can see 3 diagrams here on the top of this plot, is the direct way of verifying that top has expected standard model couplings to the Higgs bosons. In this specific measurement, CMS used Higgs boson decays to big quarks, WWZZ, gamma gamma, and tau leptons, so most copious and easiest to detect modes of the decays. And all modes of the top quark production and decays were all modes of top quark decays, not production, because production is TTH were used. And of course, extensive use of multivariate noise. It was amazing to see just recently this discovery of this unique process of TTH production with over 5 sigma significance and measurements of values of production cross-section and couplings of the top quark to the Higgs boson. The parameter of mu is basically a ratio of this measured coupling to the coupling which is predicted in the standard model. You can see from the plot on the right, first plot, that everything is in agreement for various Higgs decay modes, as well as results at different energies and different parameters are all in agreement and indicate clear observation of this important process. Not only associated production of Higgs with pair of top quarks was detected, but associated production of pair of top quarks with photon or WN photon or Z boson were also recently established. So this is Atlas results on the measurement of, for example, TT gamma, TW gamma production and its dependence upon of the transverse momentum of the photon. And on the right, similar for the production of pair of top quarks with the Z boson in the final state and its dependence upon the PT of Z. So as you can see, even for these very unique, very sort of rare processes, there is a good agreement with a standard model for inclusive and fiducial cross-sections. But this is not all, because we now know that even 4 quarks are not top quarks produced in the same event, and you can see the diagrams here, could be detected. So just recently, Atlas showed some preliminary evidence for the observation of 4 top quarks in the final state. Look, far, far away from the pairs of the top quarks, how it was discovered at the Tevatron. And very challenging because they're quite substantial backgrounds, cross-sections are small, but still you can clearly see top quarks production with 4 of them in the final state. So now let's look a little bit further ahead. So Tevatron, LHC grade discovery, very large samples, which provides precision measurements of top mass and other properties. But we are all dreaming about Higgs factories to produce large number of Higgs bosons to study them. There are many various options here, like ILC, International Linear Collector, Future Circular Collider EE options, the options in China, and some others. So, and the question, can they be used for studies of the top quark? Of course, they have to have the center of mass energy above 350 GeV. For the Higgs factory, you need a little bit above 250 GeV. But as soon as you cross the top anti-top production threshold, as you can see from this bottom plot, and this blue curve is actually at about 350 GeV, you have sharp increase of cross-section because you can produce now top anti-top pairs. And what's important is that out of all events produced, about 30% now will be top quark pairs. So it's almost background-free situation with precision knowledge of initial state. So on the right, you can see, for example, the scan, energy scan, how many top quark pairs are produced at linear collider, so like ILC versus energy. And you can see that the precision measurement of this scan, remember, the top width is about 2 GeV. That's what defines this curve. But still, measuring this curve with high precision, because energy of the colliding electron and positron is so well known, provides opportunity to improve measurements of top quark mass to approximately 30 MeV, so extremely high accuracy. And of course, we are also dreaming about next energy frontier collider. So here you can see future circular collider hadron option at CERN in 100-kilometer long ring. Luminosity will be even higher than LHC, and such collider will produce 5,000 top quarks pairs per second, and almost 500,000 of single top quarks per second. And you can see from the top on the right that cross sections now between LHC at 14 TeV and 100 TeV collider are increasing by another 2-3 orders of magnitude, especially for the single top quark production. So single to background ratio is much better. So actually such very high energy hadron collider will become really top factory. So that brings me to my conclusions. So today we celebrate quarter of a century. So the top quark is becoming mature since the discovery of the nature's heaviest elementary particle, the top quark. Hunt for the top quark required new ideas in accelerators, detectors, and data analysis. So it was not that easy. You saw sort of major construction of new accelerators, new detectors, efforts of hundreds of scientists from all over the world, as well as that was one of the first places where large international collaborations were developed and effectively operating. Top quark studies indicate it fits very well in the standard model. Extensive list of the top quark parameters measured. There are pages and pages in PDG about the top quark properties. Large mass of the top quark, as you know, sort of it might be the link to the physics beyond the standard model. Even more precise measurements are important, so we should never stop our quest for the unknown. And as I mentioned on the previous slides, LHC is a top factory for many years to come, so it's very important to continue studies of the top quark, as well as propose future colliders, which will provide unique opportunities like linear colliders or circular colliders for Higgs factories to measure top quark mass to learn more about the top quark. So the future for this by now mature particle is exciting. And let me finish on the last slide, which follows what Uli was saying in introduction. This is actually a picture of the 2019 European Physical Society Prize to CDF and D0 for the discovery and studies of the top quark. Thank you. Questions?
Yes, I guess we should applaud here. I don't know what the etiquette is, but for this nice talk. So questions.
So I raised hand. So
yeah, I'm just trying to figure out who raises their hand. But Greg, go ahead, Greg.
Hi, Dima. Thanks a lot. Very nice talk. So my question is about the sample which we have of the top quarks to the Tevatron. Clearly, LHC is leading now this field, but nevertheless, Tevatron has accumulated a large number of quarks. I don't remember the exact number, but must be over 1,000 decays.
Mm-hmm.
Now, these are very different production mechanism decays of the top quark, because it's mainly QQ bar, and also you have proton and antiproton, which makes it symmetric rather than asymmetric as at the LHC. So these forward-backward asymmetry was an example of the measurement which was largely unique to the Tevatron, although there is some sensitivity at the LHC, but not so large. So can you think about some other measurements which you could still do with this large sample, so while it's sitting there?
So let me probably, thank you, very good question, but let me start from sitting there, maybe from the end of your question. So indeed, as a part of the preservation of Tevatron data, we did store especially these high PT sort of unique samples of WZ top on tapes and on disks to preserve them for a long time to come. Now, it appeared that storing zeros and ones on disks and tapes is important, but not the only sort of what's important. So it's even more important to have access in terms of software, which will provide you access. So it's actually even by now becoming very challenging to access these data samples. So we are trying to sort of preserve these opportunities, but of course, as software languages, operating systems are changing, trying to access this data is not easy. So the bottom line at this moment, we do have various studies which are still progressing at D0. We published like 3 papers this year. It's mainly about heavy flavor, different new particles and properties of particles. But in top quark, except of combination of the top quark mass with LHC, there are no active analyses progressing. Although we are open, if someone would be excited to do something, the data are available.
Right, so thanks. So there is no real kind of good plan how to make the data publicly available because well, lab experiments are basically same age as Tevatron experiments, even older, and yet they made their data available publicly. It's questionable how good the quality of this analysis made by general public, but at least they went through the effort, and LHC, of course, is also doing this via open data in a more systematic way. So there are good examples how you could preserve the data.
Greg, this is a good sort of point. I would agree with you that Tevatron here probably didn't do as well as lab or LHC is doing now for various reasons. One of them was that it was sort of not planned from the beginning. And of course, there were a lot of concerns. Look, for example, how to provide not just the data events, which, as you saw from the talk, as you know, require understanding of backgrounds and many others, because you never know if it's top quark event or not. Look, you need statistics to make some reasonable predictions. So we're still thinking about that, but as of today, the answer is no. There were many discussions over the last, I would say, 7 years, including experience with Quira. You probably remember that at the end of round 1. And but I would say no, at this moment, there is no plan unless sort of we will try to find resources to do that.
Right, well, that's pity, but yeah, I understand.
No, you're absolutely right. I can only agree.
Thank you.
Any other questions?
I see Luke raised hand, so you should just speak up.
Yeah, go ahead.
Thank you for that great talk. That was really fascinating. I've just got a qualitative question about proton antiproton colliders versus electron positron colliders. Just looking at the graphs, it's the striking thing is that proton antiproton cross sections rise as opposed to the electron positron cross sections falling like 1/s. My first question is the explanation for that a rapid growth of the PDFs? Is that the actual explanation for it? Or what is the explanation of the rapid growth?
Yes, look, the simple
Of
explanation.
the cross section, and does that feed into whether or not one's?
The simple explanation is you're right, basically PDFs, because protons and antiprotons are bags of gluons and quarks, and at the end you can even very low X particles, and there are many of them, can be used in order to produce relatively heavy objects. So that's basically the difference between the point like plus and minus or muon, anti-muon collisions and collisions of the protons and antiprotons. That's your assumption is correct.
Okay, thank you very much.
I'm muted. Anybody else? I don't see any raised hands anymore. Okay, so maybe I have a quick question. So you showed how one can measure the top quark mass much more precisely with an E+ E- collider. Is there a difference between the circular and the linear colliders in this here?
Not much. So it's actually pretty close. So the challenge here is that, of course, linear is a little bit better, because what the challenge with the circular is that you don't know the energy of the E+ and minus beam, because electrons and positron radiate synchrotron radiation. So by the time they collide, so you don't really know exactly the energy. So you add like Gaussian distribution to the spread. But from at the linear colliders, the challenge is a little bit difficult, although deeply, and the reason is the same, is because when in linear colliders, the bunch intensities are extremely high. So when bunches are going, these electrons and positrons going through each other, electrons and positrons radiate in these very high fields of the opposite bunch. And as a result, again, you don't know exactly the energy of the E+ and minus collision. So, but if you look on the ultimate accuracies, they're very much, they're similar. They're in the range between, I would say, 20 and 50 MeV.
I see, thank you. Okay, last call, any other questions? Then let's thank Dmitri for this nice talk another time.
And thank you for connecting and for interesting questions and for listening. And I really wish I would be with you guys at Brown, yes, sort of, and can shake your hands, but I hope in the future.
Yeah, we hope that will happen in not too distant future. So let's look forward to that. Thank you very much.
Thank you and stay safe.
Bye.
Bye-bye.
Bye-bye.
Bye.